Hey there, this is me, Quint. This is build 2 going into the details behind the pumped storage video. So if you haven't seen it yet, released this, what I hope is a really popular video on pumped storage using a solar power and storing that rather than storing it in some fancy battery, that we store it in a water battery, if you will, using the weight of the water as the energy storage mechanism, if you will. Anyway, we're going to go into the details of what I learned doing that project. It was kind of cool. I actually did not know a lot about the pumped storage when I started it. Back in 2005, I think, when I was force-feeding myself German, trying to really polish that language, I saw some news articles about some proposed projects in Germany. But I didn't realize that there were several of those already here in the States. In fact, the largest one in the world, I didn't mention it in the video, but the largest one in the world it's on the border of Virginia and West Virginia in the United States. And I'll talk more about that one here in a bit. But yeah, these things are all over the place. They're just not as much used for storing green renewable energy kind of stuff. Something I was surprised to learn was that California has so much solar and wind power that they, on several days of the year, they are paying neighboring states to take their excess power. California also already sells power to their residents at a rate much higher than the rest of the states in the United States, and yet they pay neighboring states to take the excess. Now, part of that is because they have so much solar, but a chunk of it is that they have contracts with existing power companies where they've agreed to buy so much power per day, kind of a thing, that maybe if they shut off some of those fossil fuel burning plants, that maybe they'd have the right amount of solar. But either way, if they were to figure out pumped storage or just energy storage in general, they wouldn't have that problem. They wouldn't have to be, say, it just blows my mind that they're paying neighboring states to take that. That's just like, I can't believe it. So they have a number of issues to work out, but the sooner they can get to energy storage, then the way better off they're going to be. Another fact that makes complete sense in retrospect is that these power plants that are storing energy don't make any power. They're actually consuming power. And it's like, well, wait a minute, you're storing energy, why are you using it? Well, because there is no perfect battery, or even lithium cells, you're not going to get out all of the energy that you put into it. There's something lost in conversion. So yeah, here we are storing energy, but this energy storage system is actually using some of the power that we're putting into it. And it's like, well, wait a minute, that seems really rough. How can this make any sense? Well, economically, these storage systems can actually make money. And it's like, well, how is something that is using power going to make us any money? And it's one of these stock market, like, buy low, sell high kind of thing. So they will fill up with energy when the price of energy is low in the middle of the night when nobody's using it, or even middle of the day when not as many people are using it. It doesn't cost as much depending on where you live. And so they're putting it in at the cost of pennies, and then when it's high demand and they don't even know if the grid has enough power to supply everybody that needs it, they can sell it back to the grid at, orders of magnitude more than what they bought it for. So there it actually becomes an economic solution where it's like, hey, this thing makes money, it's worth an investment, and hence why we're seeing investors that are willing to pour millions, if not billions of dollars into these things, because they know they're going to pay back in the long term. Now, back to that largest pumped storage plant in Virginia, I was surprised to learn that all of the energy that's getting stored there is from the local coal-fired power plant. I'm going, wait a minute, this is supposed to be a green energy kind of thing. It's like, well, one, this was a plant that was made back in the 70s. I think they finished it in 1985, like started it in 78. But again, that one was an economic decision. They were looking at the coal plant that they had at the time, was not going to be enough to meet the peak demands of the day in the morning and the evening as people are getting up and getting ready for work, and then when they come home from work, those peaks in the demand. They realized their coal plant was not enough, and they said, well, what do we do? Do we build another coal plant? Do we build a nuclear plant? They actually looked at that. Do we build I think it was a like natural gas plant, or do we do this pump storage thing? And at the time, the price of natural gas like priced it out of as an option, and then built. I don't remember the complications associated with the coal plant, but nuclear was expensive as it is now, and it just say economically being able to run that single coal plant, and then when it wasn't needed, they could just use it to pump water up into this ginormous reservoir. That made the most economic sense, and so that's what they went with. And we say, well, wait a minute, they're burning coal. Well, it wasn't as much of a concern back in the 70s when they decided to do it, but it actually allows that coal plant. It's a smaller coal plant that can run at peak efficiency like 24/7, thereby they're actually burning less fossil fuels than they would if they had a much bigger plant that was just throttling up and down all the time, zipping around past not necessarily running at peak efficiency. So that was kind of cool. So I want to quickly dive into some of the calculations that were done for figuring out that 14,000 joules for the barrel on my roof, as well as then comparing that to the Swan Lake, I think it was, down in Southern Oregon project, and just quickly diving into those numbers. And to do that, I'm going to use one of my my latest purchases here. You've probably seen the ads for all these tablets. This is and this is not a sponsored video. This is just me saying a tool that I've been using. I splurged on one of these Remarkables. It's the Remarkable 2, and my gosh, it seemed like everybody and their dog has a YouTube video on doing sponsored type video trying to sell these things. I just got one to try it out, and I was really reluctant to spend the $600 that by the time I got everything to get it. But man, it has been indispensable for me. And I did all the calculations for this video, all the planning for the video using this tablet. And so let's dive in. I'm going to show you the calculations I did real quick. All right, this is the first time I've ever videoing this screen. Hopefully it ends up looking good in the final version. You can tell me in the comments if it looks all right. But one of those things that you just don't forget after doing a bunch of engineering school is just some of these basic things like F equals ma, or just work is force times distance, and work is energy. So when I think about the height of that drum on my roof, it's like, okay, it's force times distance, which can be, usually it's something that you're sliding along a surface, giving a certain amount of force to move it whatever distance, but it also works great for gravity, that you're just lifting it up. And of course the force is the weight, which we know in basic physics is the mass times gravity gives you the weight. And because the mass is this fluid, like, okay, well that mass is now going to be the density of the fluid times the volume. So that really works out to the density of the fluid times the volume of the fluid times gravity times whatever height. And if you haven't watched the video yet on units, I think I called it the math that engineers use most. This is right where that comes from, where I just laid everything out, where the density is, you'd think it'd be 1 kilogram per liter. The metric system is so nice. And it actually is at just above freezing, but okay, 0.997. Could I have gone 1 kilogram per liter? Yeah, it would have been close enough for what I'm doing. But a lot of perfectionists out there watching my stuff, so I got to be accurate. 0.997 kilograms per liter. And the volume we said was 200. It turns out 55-gallon drum is equivalent to 208 liters. And then gravity is 9.8 meters per second squared. Someday I'm going to do a video on the details of what that number means. And then we said, yeah, I thought it was 5 meters, 7 meters high. And so our liters cancel out, and we're left with kilograms, meters per second squared. And man, that is one you just want to, if you don't know it yet, you got to burn that into your mind, that a kilogram meters per second squared is a Newton, which is a force. And we've got one more meter over here. So it's Newton meters, which you could think of as a torque, but it's also work. So the newtons that I'm pushing whatever distance, so force times distance. And with the correct numbers in there, that's where the 14,000 Newton meters or joules, Newton meter is the same thing as a joule, came from. And let's see, where did I go? So I wanted to know what that was in watt hours to be able to compare it to a battery. The whole, hey Morpheus, how big is this battery kind of part of that video. And I struggled with this a little bit. I was like, how am I going to convert joules to watt hours? And it's super simple. I don't know why it was messing with me. I had joules, and okay, how many watt hours is a joule? And I know that, or we should know that a watt is a joule per second. So I've got the joules of energy. How fast you're using it? Joule per second is a watt. And I want to know, I want to throw hours in there. So I got to convert seconds to hours, and there's 3,600 seconds in an hour. So by the time you cancel out the seconds, it's just 1 watt hour is 3,600 joules. So now that we have these two things that are equal to each other, we can put them over each other. Again, this is from the units video, and multiply it in. Because it's equal to itself, putting it over itself is the same thing as 1. And you can multiply anything times 1 all you want. So the joules go on the bottom. I could put them on the top, but then it would just mess things up. Put it on the bottom, the joules cancel, and we're left with watt hours, and it's all a whole whopping 3.9 watt hours. Now, I looked up the capacities of various batteries, and a AA battery. Now, they tend to give you battery capacity in milliamp hours. That's what I'm looking for as an engineer when I'm working on an electronic device, when I'm comparing various batteries, is the milliamp hours. If you want to know the watts, you have to know the volts. That's another one of those, hey, if we want to know what the watts are, it's volts times amps. And here it's, if I just multiplied the milliamps times volts, I would get milliwatts. But I want watt hours. That's what I put this in. And so we divided by 1,000 in there. So multiplying times 1.5, I got 3.6 watt hours for AA. We got 1.5 watt hours for a AAA. And I thought, well, shoot, how big is a C? And I was shocked at how much bigger a C battery is as far as capacity. 8,000 milliamp hours, still the same 1.5 volts, even all the way to a D battery. So times 1.5, there's your 12 watt hours. So 3.9, it's just a little higher than a AA battery. Now, that's the amount of energy that's up there. What can we actually get out of it is another question. But that's where that calculation came from, it wasn't, Morpheus holds up the C battery, but it's actually a much closer to a AA. So if you didn't catch it, my son didn't even notice that it was me wearing the sunglasses when I held up the AA. Now looking at these Swan Lake installation that is apparently they're breaking ground this year in 2021 down in outside of Klamath Falls in Southern Oregon. And it was really tough to find the numbers. They give you these soft sort of, this thing will be able to produce this much megawatts of capacity, which to me doesn't mean anything. I want to know megawatt hours, not mega. The rate doesn't mean anything to me. I mean, yes, it's nice to know what rate it's capable of delivering at, but how much capacity is there? What can it really do? And so what I found was that, okay, 9 hours worth of 394 megawatt. So to get megawatt hours, you multiply times the hours, and it was 3,556 megawatt hours of energy storage at that when it's done at the Swan Lake facility. And let's see. So I compared that. I wrote out those watt hours and compared it to my 3.9 watt hours. Divide the two, and it was really close to 1 trillion times. So I said in the video that the Swan Lake facility will have about 1 trillion times more energy than my setup that it can store. And actually, I think it is more than 1 trillion by the time, and we'll get into that here in a second of why it's actually more than 1 trillion, because I sort of cheated on my numbers where they didn't. And when you look at the size of the reservoirs, they give it to you in this crazy number, which, by the way, I had to go, I couldn't find it on any websites. I had to go find the environmental impact study that was done. I don't know if it was done by the Bureau of Land Management, but the government agency did an environmental impact study that took them however many years to get through and eventually approve it. That 200 and something page document, I'll put a link down in the show notes here, that's where I actually got the real numbers. In there, they said, okay, the upper reservoir, they use this acre feet number, which is kind of crazy, but it's 2,500 acre feet at 6,000 feet of elevation, and then the lower reservoir is actually just a little bit bigger. I don't know if that was intentional or not, but a little more than 2,500 acre feet at 4,400 feet of elevation. And so, okay, I'm not used to working with acre feet. What an acre foot is, an acre is something like they'll say, like my house is on a 1/4 acre plot, and you go buy farmland and they'll tell you how big the land is. Okay, this is a 10-acre field. And so an acre foot is how much water it would take to cover 1 acre 1 foot deep. And I know everybody that's used to the metric system is just rolling their eyes, or they're switching to a different video at this point because you can't stand it. So I had to go look up an acre foot. It's the same thing as 326,000 gallons. And then did I put liters on here? Well, it's roughly 4 liters to a gallon. So you got to go like 3.8 times this to find out. Yeah, so let's see. So their upper reservoir, that's 2,568 acre feet, is 837 million gallons, which is 3 billion liters of water. And then I just pumped, I was going to say, into the same formula that I had before for my roof, that I have 3.1 times 10 to the 9 liters. There's our density times gravity times height, and got this crazy number of 1.5 times 10 to the 13 joules. So if you don't know scientific notation, the e to the 13 is just moving that decimal point 13 places over. And then to get to the megawatt hours, I'm throwing the same 3,600, divide by 3,600 joules to get watt hours, and then megawatt hours through a million on there. And so I got 4,377 megawatt hours. And I said, well, wait a minute. How come I'm calculating over 4,000 megawatt hours of capacity when they advertise in all their public, the stuff that's really easy to find, they're saying we have 3,556 megawatt hours. Like, well, what's the difference here? It's like, well, this is the actual gross energy that's there. But can they turn 100% of that back into electricity? No, there's some efficiency losses. We said at the beginning that no battery is perfect. So let's take this that they're advertising, what they can get out, and divide it by what's available, and it comes out to this really nice 81% efficiency. So they are, and I saw that referenced elsewhere, that they said that pump storage could do better than 80% efficiency, and that's what it is that you calculate how much energy, like the barrel on my roof has 14,000 joules, but then the question is, how much can I actually get out of that and power lights with? And the answer is kind of sad. Because this is grid level type stuff, the little losses of running things aren't as big of a percentage. And of course, they've put a lot more refinement into getting as much of that energy back out, because it makes them more money if they can. But let's take this efficiency, the fact that they're storing these this much energy and they're getting this much out. Let's do a quick comparison. We're almost done on my actual barrel storage. Come on, swipe over to the new one. So the numbers that I ran, we stored 14,200 joules in that barrel on my roof, and it took 5.5 hours to do it. Now, dividing by 3,600 seconds, it comes out to 0.7 watts is how much power that pump was actually putting into the water by, you know, the rate that it was putting it into the water, putting it out per barrel. Now I know I said we had a 50-watt solar panel that was running it, but the pump was only using 6 watts. You can't jam any more power. It could have been a 1,000-watt solar panel and it wouldn't have mattered. That pump was only able to draw 6 watts of power. It was running at 12 volts and right at half an amp. So 0.5 amps times 12 was 6 watts, and it was drawing. They advertised it as a 6-watt pump, and it was drawing 6 watts of power. But using all that 6 watts only was producing 0.7 watts of energy. So that thing with that little DC motor, horribly inefficient. You saw how hot that thing was getting, enough to just about burn my finger. That's where the other 5.3 watts were going, was making that motor hot. So yeah, so it horribly inefficient, not able to take advantage of our 50 watts, using 6 watts, only getting 0.7 watts. And then the output, I told you with that thing maxed out, valve wide open, we were getting really close to a watt, and it was probably only going to run for a half hour. I never did run it empty. I probably will do that here shortly when I empty it and take it off my roof. So if it was a 1 watt for a half hour, then we're only talking about 0.5 watt hours compared to, what did we say? It was 3.9 watt hours. So we're not, I mean, horrible efficiency for our energy storage. But hey, what are you going to get? I mean, what do you expect? This is stuff I just ordered stuff off of Amazon and threw this thing together, and hey, it worked. It was a lot of fun. I learned a ton. Hopefully you learned some of that too. Maybe there's some students out there that can do some, you know, some high school students maybe doing a project on renewable energy and talk about sources and how big of a reservoir they would have to be able to power their school for a whole day or something like that. But hey, that's why I do this, to help people that don't have access to engineers and engineering, just like I did not as a kid. And now you've got some details of this video. Hope you learned something. Hope you enjoyed it. I'll see you in the next video.